Good afternoon, gentlemen. It's a great honor for me to be presenting this keynote speech to you on the future directions of offshore research in wind. I think that renewables have never been more important than today to reduce our dependence on fossil fuels. And it's very exciting to be part of the opening of this new center at Kyushu University. I think you heard something of my background. It consists really of over 10 years in manufacturing industry, in the wind turbine industry, over 20 years involved in the development of wind turbines and in general consultancy, especially with emphasis on evaluating innovation. And since 2009, I have been involved in the University of Strathclyde, where we have around 70 and 80 to 80 students conducting PhD research on wind and marine topics. Some of the information I'm presenting today comes from some recent work I completed with a colleague on a comprehensive renewable energy encyclopedia. I was looking particularly at trends in technology and research. In addition, I'll give some focus to offshore and floating offshore, especially as of the greatest relevance in Japan, and mention some future technologies, including airborne wind and hydrogen. It's very obvious to anyone who's observed the wind industry at all that there has been a progressive growth in the size of wind turbines. For a while, in fact, for about 20 years or so, the growth of wind turbines was actually literally exponential. This is illustrated on the chart on the right, where the vertical scale is logarithmic. And this could not go on forever. And since about 2004 or 5, when the Repower 5 megawatt offshore machine was established, there has been increase in turbine size to 10 megawatts, and most recently the 16 megawatt Mingyang turbine. But the exponential growth has stopped. There was a similar pattern in the aircraft industry, and both industries, you have limits. Basically, the value of a wind turbine is related to the area for energy capture, the lifting ability of an aircraft relates to wing area, but the cost and weights are more related to volume. And this imposes economic and practical limits on how big these machines can be. For most European machines on land, tip speeds were restricted around 60, 65 meters per second. And then with the advent of variable speed technology, which could manage noise by reducing speed in certain wind conditions, somewhat higher tip speeds, 70 or 80 meters per second, were employed. The faster the machine runs, the lower the torque at a given power and the less weight and cost in the drivetrain. We see a pattern with offshore machines where tip speeds have increased into the 90 meters per second range and perhaps a little above. This is advantageous for the economics of the turbine. It could be pushed further to values like 120 meters per second, but I think there is still some concern about blade erosion and the implications for maintenance. Another pattern in offshore machines is reduced power density, which is equivalent to a relatively larger diameter in relation to the rated power of the machine. The whole logic of how much power you extract from a machine of a given size is really about the ratio of the value of energy from the rotor and the costs incurred by rotor loads, and in particular by the electrical transmission system. The cost of the transmission system is much greater offshore, and the cost of rotors in terms of the lifetime cost is rather less, and this justifies larger rotors. So we see an average power density on land of around 400 watts per meter squared, reducing offshore to values like 350, 320, a general pattern for offshore turbines. Aerodynamic research has been active since the beginning of the modern wind industry in 1980 and continues. It might have been thought with mature industries in aircraft, both civil and military, that there would be enough done on airfoil development. But in fact, the specification of wind turbines is different. Stall is sometimes useful in limiting loads. For lighter, very large rotors, sections with higher lift are advantageous. Sections with higher lift are advantageous to avoid the rotor blade sections being too big near the root. And so, in summary, the development of aerofoil sections has been active and remains active in research. If you look at the largest machines around, the permanent magnet design of generator seems to be quite dominant. There have been considerable concerns in recent years about the supply of rare earth magnets. And in some of manufacturers like Siemens, although they use permanent magnets in their biggest machines, are avoiding them in smaller machines. And even a Chinese manufacturer like Goldwind is considering systems with gearing, which not usually a high-speed generator, but systems that reduce the quantity of magnet material. There's also competition with electric vehicles for some of the components of the rare earth magnets, such as dysprosium, which is useful in for the cooling of the generator. The attraction of the permanent magnet design is in the comparative simplicity of the generator, avoiding geared systems in the direct drive solutions. This is a particularly innovative solution which achieves the gearing magnetically without lubrication. And we have a conflict here because these designs with the permanent magnets are among the most efficient, especially at lower part loads. And at the same time, there's concern about permanent magnet supply worldwide, especially because of the Chinese stranglehold on the market. There are a huge number of innovative wind turbine designs. My connection with Kyushu University, which has been over 10 years, started with an invitation from Professor Yoshida, and very quickly I realized we had a lot of common interest with the research that Professor Oya was conducting. The wind lens ducted rotor developed at Kyushu is, in my opinion, one of the most effective designs. I think the combination of an expansion area and a brim leads to a compact rotor. And I believe this is the best way to go with that type of design. On the left here is an innovative rotor being developed in a European project at Strathclyde University, where avoiding a large, expensive drivetrain, the power takeoff is achieved using small secondary rotors at the blade tips. If you look at the research papers published today, it's very obvious that over the past 20 years, no surprise to anyone, there has been very strong growth of interest in offshore. And offshore, although it's still a relatively small proportion of the total installed capacity in the world, is the area of greatest growth in research. And within offshore, floating systems that is also showing the greatest growth. So this reinforces the relevance of the work that is going to be undertaken at the new center in Kyushu. We now have floating projects and floating wind farms. I won't say much about this, especially at Fukushima. You will know a great deal more than I do. But the development is now seriously underway. For that technology, I draw attention to some key areas in the floater design. The semi-submersible design is definitely dominating the market at the moment. But I believe the key to the most effective design is to integrate the floater with the wind turbine structure. And also there are new concepts for floaters which involve suspending the ballast mass rather than them directly filling elements of the structure. I'm not an expert in hydrodynamics, but it seems to me that this is a very active research area and is going to be important for getting costs down. What I would like to emphasize is that when I started, especially looking at innovation for the UK government in the 1990s, rather than simply look at some ideas and try and compare them, I asked myself the question, what is the basis of effective innovation? What is the logic of systems that will really reduce the cost of energy? And two things were very noticeable. One, that there's a mismatch between energy production, which comes in moderate and light winds predominantly, and the cost in a wind turbine, which is driven by defending the turbine in the higher wind speeds and in extreme wind speeds, in the case of Japan, typhoon conditions. The other area is a simple observation that the value of a wind turbine is in the area exposed to the wind. That's the source of the energy. Everything you do to support that area and to extract the power is producing cost. So the ratio of area to cost is a key parameter in increasing that is a design principle for innovation. This led me to the multi-rotor system. You can have systems with a few turbines, like the Aerodan turbine, which the twin turbines are producing 15 megawatts. And it's a very nice design. And the integration of the structure for the twin turbines with the floater leads to a light and promising design, promising to be low cost. The systems with a large number of rotors are different in character. They really exploit the benefit of having a large area but a small volume of rotor nacelle assembly materials and cost. So there are huge CAFEX savings in what is normally a major cost element of the wind turbine, the rotor and the drivetrain. But perhaps even more important is the possibility for standardization. If you imagine large wind turbines, the largest ones think of the development time. If you have an idea for a better blade, what sort of costs and resources are needed to make the biggest blades? How soon will that be in production? Compare that with systems based on small components, where quantity production can lead to faster learning and reliability. The other factor with multi-rotors, which we see in the wind catcher system, which has been is being developed in Norway and supported by investors with very deep pockets. That system is nominally 126 megawatts. That's a unit capacity which you cannot dream of achieving with a single turbine. And it benefits O&M tremendously to have fewer large systems per installed megawatt. It's conceived of as a floating system I was not directly involved in the design of this system, but I was involved in design review and evaluation and guidance on the design. There are two options basically for the yawing of the thing. One is to have a turret, a moored turret, and the system can rotate around it. The other possibility is that it can simply yaw, taking up a downwind attitude by drift on catenary lines. This means that you avoid the need for any specific and potentially expensive mechanism to enable the yawing of the system. I have recently been involved with the European team on the development of a multi-rotor system based on vertical turbines. I don't have time to explain all the logic of this, but the vertical turbines, which are normally less efficient than horizontal turbines, in a blockage situation side by side can generate extra power. If they're high aspect ratio with long blades, you mitigate tip loss. They're naturally supported in a rectangular structure, which is good for maintenance and so forth. And the system is particularly good for O&M. Again, you see some other illustrations, and these are about integrating floater design and the wind turbine design. If there is any issue regarding conventional turbines and particularly multi-rotor turbines offshore, the one above all that is of critical importance is the operation and maintenance. It's a higher proportion of costs offshore. And particularly at Strathclyde University, for the multi-rotors, we have been developing detailed modelling. And I have done some work for leading manufacturers such as Siemens, and it appears the key is the management of minor faults. In multi-rotor systems with small turbines, you can have systems, efficient systems for handling the turbines, avoiding the use of jack-up vessels. But it's very important with a lot of turbines that you can deal efficiently with minor faults or avoid them by introducing extra redundancies or more reliable components. We see in also offshore the possibilities of using drones for inspection and all sorts of adaptations of artificial intelligence, such as digital twins, can improve the management of the systems, and is certainly a very active research area of general interest. There are now a number of projects looking at offshore hydrogen production. There seems to be some consensus that the optimum solution will be to produce the hydrogen locally offshore rather than transmit electricity to electrolyzers based on land. The projects in Europe are very naturally looking at the detailed design of electrolyzers and all the necessary equipment and how costs can be reduced. I would add to that a simple observation that if you can decouple the production of energy from electricity demand by having a storage medium such as hydrogen, then the same amount of energy can be produced by a much smaller rotor with a larger generator. This wouldn't be effective usually because the rated wind speed would be high, the energy would be produced for a few hours in strong winds rather than frequently in lighter winds. That wouldn't suit electricity demand, but if you can decouple from demand, then the turbine can produce electricity locally, very, very cheap electricity, which helps the problem of improving the electrolyzers and getting the costs down there to produce hydrogen at a competitive, commercially competitive value. We see here a large number of institutions, some involved in prototype manufacture, some in research around the world looking at airborne systems. I would ask you to cast your mind back. When I started in 1980, it was scarcely credible that wind turbines would be useful for an electrical network. By 1990, land-based technology was established, but offshore was considered far too expensive. By 2000, offshore was in progress. Floating was still considered problematic and too expensive. And so on the story goes. Floating is now established. There are advantages in available resource areas and in the not being tied to specific seabed conditions. And floating wind farms are now established. Airborne prototypes are operational. Airborne takes me back, I'll just very quickly get back to this slide. You have the opportunity to take the machine out of the air if severe storm conditions are approaching. This means that you're much improving this mismatch between the design loads and cost and the energy production. You also get access to to higher wind speeds at moderate altitudes of 1,000 meters or so. So it's another interesting area for offshore research. So to conclude, very obvious that offshore dominates present wind energy research and that floating offshore is the fastest growing area. It's now all about offshore increasing reliability and getting costs down, and especially in the integration of floater and support structure, I would suggest. I've indicated the promise of multi-rotor systems for upscaling the large unit capacities, and would emphasize that it's not simply a matter of modeling O&M and getting the logistics right. It is designing the system from the outset in terms of both margins for reliability and O&M, how you're going to handle components and so on. And there's plenty of scope and need for further research there. So I hope this is going to be a useful outline for you, and thank you very much for your attention.